There we go. Hello. I think there's a few of you out there, so welcome as always. I'm always happy to have a few people join me for the live stream. Um, yeah, so this week is one of our more straightforward weeks in that we don't have a lot of material to cover, though I'll take advantage of the opportunity to um, explore the flags register a little bit today. Um, yeah, so we'll look at some of the just a couple examples of your work on the labs from last week, which were like 99% and plus of the labs that were submitted were just good, solid work. So um, I was very happy for that. It makes my life easier and it also makes my life less sad. So that was much appreciated. The improvement in in the global quality of the lab submission. So keep up the good work. I appreciate it. All right, so today we're just going to do the add and subtract instructions. We previewed those last week, so this week we'll tease out a couple more details about it. Also talk a little bit just about random number generating, and that's only because it offers us a chance to revisit how many bits it takes to represent data and where those bits goes kinds of issues. So we'll use rand as an excuse to do that. And then finally, I'll just leave off with some tips for the lab for this week, the one that's due on Sunday. And then probably I'll go peek at the project. But in this class, I don't do the project is not asking a whole lot in terms of purely assembly type of stuff. So I hope it's true that everyone is well within their skill set to implement the project. So I don't feel the need to bother you and waste your time talking about it. You certainly are free to use Piazza, Canvas Inbox, office hours to talk about your project. We had a person who came to the drop-in office hours last week who was like exploring a lot of the higher level functionality of the HLA language, and that person is getting a really good project result from it. So that's where we're at. I'm gonna, yeah, I think I'll just show a few demos from last week's labs real quick. I hope you guys don't get tired of that. I just find that there are enough people who give me feedback that they like to see get a kind of a glimpse of other people's work in the classes that they take, that it's worth the time to do it. I've only got a few this week, and it's because there were so many just really good ones that it was hard to pick from. So I just kind of every so often picked one and put it among my demos. So let me switch views, and we'll do that part first. Is just show off your work from last week. Seems all right. What do we have in here? I'm just going to make a test file and do it that way. Okay, so a few demos. I'll just run through them real quick. So this is a person who explored the controlling the colors in the output, which is just kind of a cool thing to do. I hope that the experience for those of you who are trying these extra things is that it is a confidence booster, that you can engage with a new programming language with its own set of libraries and actually use those things to create software. Okay, so yeah, in chat, Druid says that they like to see the demos. So thanks for that feedback, Druid. It is if everyone's just getting ground down by it, of course I would stop. But I think it's helpful just to see kind of what people saw in a lab. So this person went after doing the colors, and which is cool and not very difficult. There is one catch about doing the colors is that. And we had a Piazza discussion about this last week, that there doesn't seem to be a way to restore the colors from within your code, and that's fine. Just go nuts with the colors. Worst thing comes to worst, I have to shut down the terminal and restart it, but usually just shutting down the program and clearing the terminal is enough. I forget what this program was. Oh yeah, the number guessing game. I also like that this person kind of put in kind of a little bit of theme or attitude into the output. So coming in a little hot, which is quite cool. I got it in 2, which of course is because it's a random number. I'm not that good. It did happen twice, by the way. So I evaluated about 50 of these, and twice. So what I did when I got them is every person's, I ran it through 2 times, sometimes a 3rd time, so I could see all the counters working. And then twice. So that would be then that I did about 150 runs of the number guessing game. And twice I got, when I put in 50, that was the correct answer out of 150 runs, which is a pretty high proportion. Okay, so anyway, that one's quite cool. That's my fault. Because of that right there. So this one is fun just because it also kind of introduced a little bit of attitude. But what stood out for this one, and this is the only person who had this particular feature, which was a very cool feature. I appreciate this. This person allowed you to put a cheat, which is basically that the program would show you what the number was, and then you could go kind of playing around with it. And I really liked that feature. That was a super cool touch to have this cheat option. So now I know it's 66, so I can say 65, and I can test whether or not it says too low. And I can test 67, and that's going to tell me that it should be it's too high, and then I can hit 66, and that's exactly right. And then I went ahead and made sure that without the cheating option, that was actually true, and yes. Anyway, you get the idea. Very nice touch. Very cool idea to let me have the cheat, which made my life easier, and also is just kind of a cool feature to have. And let me see what stands out about this one. Higher, lower. Where am I at? 18. Let's see. Oh yeah, so this person had a feature. I'll just show you in the code real quick. So this person's special touch was that they added a decision tree at the end of a run of the game and changed the message based on how many guesses that you took. So that was a very cool feature as well. And I wasn't paying attention the first time, and it took me like 9 or 10 guesses because I made a mistake somewhere, and I got the interesting output, and I thought, oh, that's interesting. I should try and see if I get a nicer message from the code, and I did. And then of course I went and looked at the code, and that's a very cool touch. So good on y'all. That was a pretty cool thing. Okay, so sorry, I'm back out of that, and I can see what's going on in the chat. So, so Druid asked, "Am I doing this manually, or do I run it with another program?" And I could probably figure out a way to write code to interact with it, but no, I did it manually. So when I evaluate your programs, I do it manually. In part because one of the kinds of things that I'm looking for, just to try to kind of steer you in a good direction, is if I see weirdnesses in your outputs, or if your prompts for inputs don't make sense to me, I can at least sort of make a recommendation to you that you could improve your program output and make better prompts. So I'm kind of carefully watching these things as I run through them. It takes forever. It's not my favorite part of the job. So yeah, I do run all of them manually. And then I had projects this week. So I ended up doing in 4 sections that I had to do interactive runs with. I don't know. My guess would be I probably did like 1,000, maybe 1,000 run throughs of various different programs that I saw to expose bugs, to experience user interfaces and stuff like that. Yeah, that's tiring work. Anyway, so it's cool when I come across one where someone has taken a little bit extra time to do something interesting, because it's a good break for me. And it's especially a good break for me if that person has done something to make my life easier, which is good advice in life, by the way. If you want people to do things for and with you, make it easier for them to do that. And I would argue anyway that I suspect it's more likely they will be more helpful to you. So that's not a way to get a better score against the requirements, but it is appreciated, and I do like to celebrate it when I do the demos. So at least you guys know that I notice and share them with you. Okay, so I'm going to switch back, and sorry about this switching back and forth a little bit, but or do I want to yet? No, let's just do some add and sub, and then I'll switch and go dig around in the details a little bit more. So that's all we're doing this week is the x86 add instruction and the x86 sub or subtract instruction. These instructions are the same in HLA as they are in x86 assembly. And in fact, HLA does not have high-level arithmetic operators in it. So you can't use the plus sign in HLA. You have to use the add instruction, which is one of the ways that HLA kind of steers you toward the assembly style. Actually, I can just gut this out. Let me save it as a week 5. Okay, so I'm leaving up my virtual machine, and the reason I'm doing that is because I want to talk about the add instruction. I'm just going to do it in code. So the things that we're on the lookout for when we do the add instruction are, do the sizes of the things being added together match? You should get errors if the sizes don't match, but it's something to pay attention to because getting even compiler errors is still an unpleasant experience. And then also, what do we do if we're trying to do math with 2 variables in the mix? How do we deal with that situation? So you'll see on my agenda that it says something about mem plus mem. What line is that on? It says mem plus mem on line 13. I know this is kind of dated language to say middleman registers, but your readings, since they are also, assembly is just kind of an old school thing to do. So your readings are going to talk about middleman registers. So I'm going to do the same thing so that when you see it in the readings, you know that I'm talking about the same thing. So we need to be mindful of the sizes of things when we're doing arithmetic. We need to be mindful of the limitations when we are trying to do arithmetic with 2 variables as opposed to 2 registers, or as opposed to 1 register and 1 variable. How does it work with 2 variables? And then we'll also add in fact, let's just change the agenda to say that. Let's also, I want to add in a short look at the carry flag. What is the carry flag and how do we use it? When does it become active? Okay, so a lot of stuff. All right, so the standard stuff, I did not put documentation just to save the screen real estate. All right, so just a basic program. We're going to add some variables here. There is a scope and a lifetime issue about static variables. So the scope of a static variable in HLA is global, and that's unavoidable because it is also a matter of the lifetime of a variable. So if you have a variable, if you have data stored in a variable and you want that data to live for the extent of the program run, life is a lot easier if you put it in a static variable. This violates all kinds of high-level programming rules, but we're not doing high-level programming, so we get some, we are sort of loosed from some of those, what are considered good high-level programming styles, like passing parameters and returning values from functions and never using globals. We're going to use globals, and we're going to use them often, but not very many of them. The registers themselves are kind of act like a global, by the way. The problem with registers in terms of trying to store data for any amount of time is that they are highly volatile. volatile. Registers are volatile in assembly language programming. And what we mean by that is they are constantly being written and overwritten as the processor does its work. So you have to be very careful of the registers, because even while your program in its self-contained form is running, every time you fire off a call to a library function or one of your own functions, often when you're doing various instructions on the processor itself, you are writing and overwriting registers. So registers are not good long-term storage options when you're writing software at the assembly level. You want variables for that. Registers are very good for very short-term kinds of things, but not for long-term things. So we use static variables largely because their lifetime is the entire run of the program, but then we also understand that they're also globals. Yeah, so that's where we are. So I'm making a couple of static variables. These will be alive for the run of the program, and they will be global. Int. We're not doing int in here. I'm going to do a couple of uns8s. In HLA, these are automatically initialized to 0 for us, unlike C++. Yes, so Druid has a good way of describing what I was just talking about in a summary form. So registers are great for short-term storage. For long-term storage, you want variables. Yeah, that's very well said, Druid. Okay, so there's a couple of uns8s, which means I will be able to, in some way, do math between them. And this is another thing that I'm just going to remind you about. So these are in RAM. That's what makes these static variables special here, is that they are being stored in the computer's RAM, which is also why they're less volatile than the processor. So they have their own little reserve space while the program's running in RAM. The other thing to remind yourself about is that declared variables with integer data types, when you print them, they will print in base 10, which is convenient because that's what most humans expect to see on the screen is base 10. If you put data in a register and you print it, the register, it's going to be hexadecimal unless you typecast it. I think maybe there was one person who was printing some counters out of a register and forgot to typecast it on last week's lab. So it's just something you're on the lookout for. It's pretty obvious when you have accidentally printed a register that you meant to show as decimal and it's showing up as hex, because it will have the wrong number of digits and often the wrong value on top of that. So be on the lookout. Declared variables with data types, like the unsigned integer data types, will display in base 10. Once you move data into a register and you print that register, you're going to get hex. You can override that behavior in HLA by typecasting the register to be the type that you want it to be, and the act of typecasting it will cause it also to show in decimal. Okay, so let's load them up with some data. and then add them together. Now I'm going to purposely do some things wrong here today so that we can examine the error output, and then hopefully you'll be better armed when you see these kinds of errors. You'll recognize them from what I've shown you here. So I'm going to try to add x and y. So the HLA ordering of these arguments is that the first argument is called the source, and the second argument is called the destination. So if we were writing this as documentation, we would say add the source to the destination. What that really looks like, though, is the destination equals the destination plus the source. So let's keep that in mind about add. Where the ultimate result goes to is the right-hand argument. In this case, our y. So what we are saying here is y equals y plus x, and you just need to get used to that. There's one exception to this, by the way, in HLA, oddly enough, that we will see later in the semester. But until we get to that point, and I draw your attention to it, the left argument is the source, the right argument is the destination. So this will add x and y together and store the result back into y. Now this is wrong as it is right now, or at least it should be, and I should get an error for it. But that's what I'm going for, is how do I make y equal y plus x? All right, so now let's, there we go. What are we, week 5? Okay, so I am getting an error on line 16, and the error is super not helpful. It just says expected, parentheses, missing parentheses. That doesn't really tell me anything about what's going on. The problem, though, is that I'm doing memory to memory. Which you know this from comparisons already, so now we're seeing it doing arithmetic. You cannot do memory to memory things on the x86 processor. The x86 processor will not allow you to do 2 fetches of data from RAM for one instruction. It will do one memory thing at a time. So I have to comment that out. That is not legal. So how do we solve this problem? We solve this problem with a middleman. So I can't do add x comma y because I get an error, even though HLA is not actually telling me what the problem is. It's on line 16, and the problem is I'm trying to do a memory to memory thing. You can't do memory to memory things. In almost any case, you can't compare them. You can't do math, memory to memory. You need a middleman. Yeah, so perfect, Druid. To create a middleman, you move one register or both to one value and or the other value to a register, perform your math, and then put things back where they started. So we have a whole bunch of choices here. But Druid in chat is exactly right. We need to copy the data from one of these memory locations into a register, do the math, and then put things back where we found them if that's required. So in this case, the least amount of work possible that we could do is to move X into a register. I'm going to move it into AL, which is usually just what I default to. But it's also commonly used as an accumulator, and that's probably because it's AL. But anyway, the accumulator simply means it's a place where we do and accumulate the results of calculations. So let's move X into AL, and then let's add AL to Y and see if it will let us do that. So it's the same thing as adding X to Y. So now what we end up with is Y equals Y. Oops, I'll comment that out. Y equals Y plus x, which I've copied into AL. So it's not actually x, but it's the value of x, and that's okay because I wasn't going to overwrite or change x anyway. I want to change y. But let's see if HLA will let us do it that way. Okay, well, it compiles. So that was a pretty easy situation to deal with. I'll use a middleman for the y so we can see the difference, and then I'll sort of ask chat to help me. So it compiles, and then we'll confirm. So I'm going to say x, and I will get x printed out in decimal for free because it is an UNZ type, which means that HLA will print it in base 10. Plus y. So it's the same, the value of x didn't change. It's just I copied that value into a middleman register so that I could do the math on it. So x didn't change, so I can still use it. Y is a problem because I just overwrote y. So here's how I would deal with this situation. Simply do the output before I change y. So I'll go ahead and print out x plus the old y, and then equals, and then I'll just wait around until I can print out the new y, and then a new line character. Should work out okay, I think. We're looking for the value of 3 here, because 1 plus 2 is 3. So notice this is just sort of the little programmer's trick that I used. I could have used another middleman register, but it was way easier to simply print out y before I change it with this add instruction, and then print it out again after the add instruction has changed it. So let's see if that works. Should be 1 plus 2 equals 3. All right, so there's 1 plus 2 equals 3. So Druid's idea for using a register and making a copy of the value as a middleman works perfectly. Let's try it. So now y is 3 and x is 1. So let's do so this time I'm going to use a middleman for y just to kind of see if there isn't some, if there's a difference in what that would feel like. So in chat, you could. So Druid asks, is there another way? So yes, Druid, you could create a third variable. Now I'm purposely making my life more difficult for the purposes of experimenting with these instructions. But Druid asks in chat, might we create a third UNZ variables to store these results, and then we don't have to sort of have the weird print half of it, do the math, print the other half of it situation. And I would say that if I were implementing software where I needed to do math like this pretty frequently, and do these kinds of outputs, then I would definitely create a third variable and clean this up. For a very small demonstration, I might not bother myself. In this case, I didn't. But yeah, you're right. In a real program, you might see this and think this is just going to create a mess somewhere down the road, and maybe a third variable would let me clean up my code, clean up my outputs, and that way I'm much less likely to introduce bugs along the way, and that's absolutely true. So no, it's a good question and a good point, Druid, because if you're making real software, sometimes you will use more memory because you can make your code read and be maintained more easily, and that's a very good trade-off, in my opinion, is to consider adding an additional variable or two so that when you're reading your code, it is way cleaned up and you don't have this kind of weirdness going on. But yeah, in this case, I'm purposely making it painful so that we can kind of explore these instructions. Okay, so let's just see what it would feel like to use a middleman for y, just to see the difference. So this time I'm going to move y into the middleman. Notice here, by the way, is an example of AL being volatile, because I used AL for this sequence of instructions, and then I'm going to reuse it in this now following sequence of instructions. And that's just an example of AL being highly volatile, meaning that it's used and overwritten constantly by all sorts of instructions. Okay, so let's see what happens if we now do this with y. I'm going to do something wrong again and let you guys catch it. So this time I'm going to move y into AL. I'm going to add x to AL, which is AL, y, which is AL, equals y, which is AL, plus x. I guess we might as well mirror this. Sure. Okay, so I did something wrong this time. So I'm still doing the same problem, but now it's going to be x, which is 1, plus y, which is 3, should equal 4. And I'll run it while you guys are thinking about what it is I screwed up here when I'm trying to use a middleman for y instead of x. So I have made a mistake somewhere in lines 26 to 29. It's not a won't compile kind of mistake, but it is a won't work kind of mistake. Close. So that is technically, that's correct. Isnam is correct. So I'm not seeing the new y. I'm seeing the old y. So I could, Isnam, print the AL here. And I'm still doing something wrong, and you guys will see it now. So what have I done wrong now? You can kind of see it on the output, which is how I catch it when you guys do it, typically, is in this very way. So correct data, but the output looks slightly off. It's in hex. Nice one, Islam. Anna Lou, it's in hex. So, and that's because it's a register. So I can typecast it to be an UNZ8. And the act of typecasting the register will get me my decimal back. But there's still something not quite right. If what I wanted was y equals y plus x, there's still something not quite right here if I want y equals y plus x ultimately. So I want y to be overwritten with the new value of adding itself to x. So something's still not quite right here. And I'll give you a hint. I skipped a step or missed a step. Nice, Druid. And Isnam. Yes. So if I'm using a middleman for y, not only do I have to do a move to load up y's value into a register, but when it's all said and done, I have to move the value back to y. Then I can print the new y down here. So the point of all this is when you are doing math and you are using a middleman because you can't do memory-to-memory things in x86 assembly, what part of the operation you choose for your middleman part can make you have to do more steps There's nothing wrong with doing more steps, but you just have to pay attention because in this case, if I use a middleman for X, it's one less step than if I used a middleman for Y, and it's something that I have to pay attention for. Because if Y is supposed to receive the ultimate result, then I have to copy it out, do the math, copy it back. So just be on the lookout for that kind of stuff. Okay, so I'm going to switch views. That's pretty basic stuff. You can also, let me just do some things that probably are obvious. So can you do something like this? And reason yourself about it. In fact, let me move it. I'm going to do it up here instead. So can I do this? So line 17, can I add AL to 100 like that? You could also hack this answer and say, I don't know, compile it if you want, which is a good way to find it out. So correct, Islam is correct. So the problem with 100 is that destinations have to be places that can store data. So the destination cannot be a literal because the destination is where the result is stored, and it doesn't make sense to store a value into 100. That's kind of backwards, right? So that's a kind of a goofy one, but you cannot do that. So be on the lookout for that kind of thing. In fact, let's run it and just see what the error looks like. If in doubt, compile it and let's just see what the error looks like. Okay, unexpected int constant near 100. So it's seeing a literal integer or a constant value integer in a place where there shouldn't be one on line 17, and that's that very bit. So no, you can't do that. Can you do 255 to AL? This one has that other trick in it to think about. Yes, you can. So Linkridge is right. You can do that. Can you do 256 plus AL? Linkridge is correct again. No. So Druid is on to where I'm heading with this. So the compiler is going to catch line 19 because of the size of the value can't be paired with an 8-bit thing. So expected an 8-bit ordinal type in the constant. And all the compiler is really saying is 256 is not 8 bits, but AL is. So those two can't go together. Now, Druid is anticipating where I'm going with this. So you can add things that won't fit. You can add up to a result that doesn't fit. Line 18 works because 255 is an 8-bit value. So x86 assembler is not going to check your results for you. It will check your inputs to an instruction, but it's not going to check to see if the results are valid. And in fact, the processor is designed to signal those circumstances, but the compiler can't check for that. Okay, so that's anticipating where we're going next. So I'm going to comment all of those out. And then we'll try the next thing down at the bottom. But let me switch views so we can read some documentation here for a moment. Okay, so if you do a Google for x86 add instruction, you'll find a whole bunch of pages that offer documentation. Um, this is just one example. You know what? Maybe I'll capture these and I'll add them to the notes. I'll add this to the lecture notes so that you can find the same ones that I was referring to. Okay. But anyway, we're going to stop on this idea for a moment just to get you thinking about it. So you cannot pair a literal or a constant integer value that can't be 8 bits with an 8-bit register or variable. So 256 cannot be 8 bits. You can't pair it with AL. 255 you can, because 255 is a legal 8-bit value. The problem is, what if I happen to add 255 to AL and AL is anything other than 0? What happens? So we're going to look into that. What happens, and can we detect it in our code and do something about it? The answer is partial. We can detect it. We may or may not be able to do anything about it, at least nothing meaningful. Okay, so here's the add instruction. It's got a whole bunch of kind of scary stuff in here. We're going to scroll down to the thing that I'm super interested in. And another thing you're going to notice here is this documentation is reversing the arguments. So this documentation, this is called the Intel syntax. We in HLA use the AT&T syntax, as it turns out, where the destination comes second. So don't get hung up on the fact that this looks backwards. How do I get immediate or literal values on the right-hand side? In HLA, we can't, because our arguments are reversed. But what we're interested in, so I'm just going to get past that. What we're interested in is this description. Now we can sort of see the flags affected, but we're going to find what we want in the description. So this adds the destination operand, which notice it says the first. That's not true in our case, because we're using HLA, which follows what's called the AT&T syntax, which is in reverse. But anyway, it adds the source and destination operands and stores the result in the destination. We've already demonstrated that with the add instruction. The destination operand can be a register or a memory location. Check. The source can be an immediate, which I've been calling literals. So just an actual integer value, a literal value. An immediate is what you'll often see it referred to in assembly documentation. Constants is what the HLA compiler calls them. So the source operand can be immediate, a register, or a memory location. We've also just shown all of that. Two memory operands cannot be used in one instruction. We've also gone and proven that as well. Hold on, I'm having a screen messiness to clean up here. Okay. We're not going to worry about the sign extending. You're going to see that soon enough. All right, so the add instruction performs integer addition. Check. That means, by the way, it does not add floating point value types together. That's a different instruction. That's all that's really saying. But we're not worried about that, because we're only actually doing unsigned integers right now. Okay, so this is the important part for what we're going to try next. So the add instruction evaluates the result for both signed, we're not doing those yet, and unsigned integer operands. That's what we want. And sets the overflow flag and the carry flags to indicate a carry in the signed or unsigned result, respectively. Now that's hard to read, but almost all of them are written something like this. So this word respectively means that we would pair the second of these, so unsigned integer operands, with the second of these, which is the carry flag. So we're going to go look at how to do this in HLA code. The carry flag is 1 bit in the E flags register. So what happens is, if you do an add instruction and the processor notes that the result wouldn't fit in your destination, it actually flicks that one bit on in the E flags register, and you can immediately then go test it to see if that happened, which would tell you that you have this error situation. Oh crud, the result didn't fit in 8 bits anymore. So we're going to play around with all of that. That's hard to read, but for us, what's interesting is if you are adding in unsigned integers, the carry flag could be set, which would tell you that the result didn't fit. It carried over the bounds. So that's all we care about for the rest of this stuff. Now let's go switch our views and play with that in code. And it already locked on me. Oh well. Okay. So I'm just going to leave all that stuff alone. So now we're going to do so we're going to set up a situation first where this doesn't happen and then where it does happen, just to see the difference. So let's do some resetting. So we're going to move 0 into X, and we're going to move 255 into Y, and then we're going to move X to AL. So this is our setup, and then do the add. Okay, so my setup is simply I'm going to make X be 0 and Y be 255. Those are both perfectly legal for 8-bit unsigned values. Now I'm going to use a middleman for X like we did before, and then I'm going to add the copied value of X, which is now an AL in the middleman, to Y. And then I'm going to look and see if the result fit or not. So I can actually, in code, check the E flags register for that specific bit, the carry flag, and that will tell me whether or not the result fit or it didn't fit. So the way you do that is really cool in HLA. You say if at C, which is the way in code you say if the carry flag has been set, that tells me there was a problem. So here is us checking the carry flag. Why the carry flag? Because the documentation tells us if you are adding unsigned integers, it's the carry flag that will signal to you that the result was too big. So that's what we're doing here. We're going to add 0 and 255, storing the result in Y. And then immediately after we do the add, we go check that one bit in the E flags register, the carry bit. If it is set, this is how you code that. If the carry flag is set, the result didn't fit. And then our else part would be actually you got a good result and here it is. So hopefully everyone knows what's going to happen here. If we add 0 and 255, does that fit in an 8-bit destination? Yes, it does. So that one kid is right. 0 and 255 is 255, and it's the maximum, but it fits. So what we should see is that the result is 255. And we should not see that the processor flagged an error state. So there's the result is 255. That's as expected. Okay, now let's do some different setup. So let's move 1 to X this time. And I know I could do this in different ways, but I want to keep showing you the middleman and the middleman and the middleman. That's why I'm doing it sort of the long way. So now we're going to put 1 into x. And now let's do the add. So we'll copy the x into AL again. And we will add AL to Y. And then we will immediately check the carry bit. And let's print it out just for fun. The dot in there so it looks decent. Okay, so the second setup, we're going to put 1 into x, and then we're going to use AL as a middleman again. We're going to add 1 to 255, which will yield 256, which means they don't fit. And the processor is going to actually mark that condition using the flags, the carry bit of the flags register. So we are testing that carry bit. Did the result not fit? This is what would tell us that. If it didn't, we're going to print a message that says, hey, the result didn't fit, and this is what Y looks like now. Semicolon there. So this is a harder quiz, maybe. So this is a 2-part question. Will this result fit? Yes or no? And then also, what is Y after this is all said and done, which is a trickier one. So will it fit, and what will Y be? No and 0 is correct. So Isnom is right on it. This is going to be a result of 256. That will not fit in 8 bits. So the processor is going to flag that one, which will allow us to detect it in our code. And when we print out Y, we will discover that the process of getting too big causes the value to wrap around to 0. So 1 too big wraps around to 0. 2 too big wraps around to 1, and so on. So yes, we should see that Y is 0, but we're also going to see our error message saying, hey, that did not fit. So let's see. We're going to see if I can read this question and understand it. So if all of the 32-bit registers have values in them, would that confuse whether you could see if the carry flag was tripped? No. So the carry flag is volatile as well. So the way the carry flag works, though, is it is probably being altered by the most recent instruction that was executed. So when you do an add instruction, as long as you immediately check the carry flag, then none of the other stuff going on is going to matter, because that immediate check of the carry flag is what the add instruction did to it, and nothing else going on the processor will affect it. Now, if you run the add instruction and then you use another instruction after the add before you check the carry flag, then the other things going on in the processor can have changed the state of the flags register, and you won't be able to detect your error. So I'm not sure if that answered the question or not, but no, what's going on in the other registers in terms of the data being stored in them won't have any effect, but running another instruction before you check the carry flag definitely will have an effect. Okay, so did everyone see that Isnom was right? This one did not fit. We knew it wasn't going to fit because it was going to be 256, and Isnom was also correct in remembering that what happens is it wraps around on itself and then comes up from 0 again. So that's exactly what we would have expected. All right, one more switch of views, and we're probably going to finish early today, so that's probably welcome news for you guys. So let's go look at the sub instruction. Remember that these pages are presenting the documentation with Intel syntax, which means the destination is backwards. We use AT&T syntax in our class, which means that the destination is on the right. So source, destination. Okay, so I just came straight down on the sub page to the description, and then we'll kind of just read through it and see what we can make sense of it. So subtracts, stores the result. So subtracts the source from the destination and stores the result back into the destination. The destination can be a register or memory location, so just like the add instruction. The source can be an immediate, constant, literal, or a register or a memory location, just like add. You can't use two memory operands in one sub instruction, just like add. Not going to worry about the sign extending yet. We'll see that when we get to signed integers. Performs integer subtraction. And again, that's just to remind the programmer that if you're doing floating point subtraction, that is actually a different set of instructions. So only integers. So here again, it evaluates signed and unsigned. We want the second one. Sets OF and CF, but we want the second one to indicate overflow. So same for sub. If the sub result doesn't fit, then the carry flag should be set. And we're not going to worry about the sign flag because we're not doing signed integers yet, but that one will be interesting to play with when we get negative numbers into the mix. Okay, so sub is basically the same, understanding that it's going to be subtraction. Why did I do that? Oh, it don't matter. Close my sub page, but I was switching back anyway. Okay, so now we'll set up some subtractions. I'm not going to go through the same long middleman kind of thing because it's the same stuff, but you're doing subtractions now. So let's just explore the carry / overflow detection just to see what that feels like. Yeah, so that one kid in chat asks an interesting question is, if you have a user, and let's all be honest, every user is our biggest bug that we can't eliminate from our software. If you have the user providing input, how do you deal with the user kind of being a goofball? So yes, and then proposing that, do we limit the user's options? Do we still kind of detect and report errors? So within the limits that you are able to do it, you should limit the user's ability to screw up your code. So that often in our class at least means limiting them to a minimum and maximum range so that the user's input doesn't screw up the math that you want to do in your program. So if you can control the user's input by limiting that input, that is a great way to deal with that problem. We're going to have situations on our second project where we don't have that control over things anymore. And the way we will deal with it is simply to flag the error so that the user knows that something is wrong and we can't fix it. So I know that's not the most satisfying of answers, but if you can filter the user's inputs by limiting their ranges of input values, that is the best first step to try to prevent this from happening. But there are going to be situations from time to time where the nature of the program you're writing, there's limits to what you can do to stop your user from being dumb. And in that case, we'll probably just detect and report errors and leave it at that. So if the user puts in the wrong data type, we are very soon going to deal with that. So we're going to use HLA's higher language capability, high-level programming language capabilities to deal with the user putting illegal values. And that's coming up very soon. So we'll have to handle both of those situations very soon. There's illegal values. You put in a negative number when I needed an unsigned number, or you put in a string when I wanted a signed integer. And then there are ranges of values that we need to filter for when we can as well. Okay, so let's do a sub. I'm going to do some setup here. So let's move 1 to y, and we will move 1 to, well, I'll do x there, and I'll do y here. And then we will do the sub, and then we will detect any problems if they happen. So same idea, I'm going to use a middleman. So I'm going to copy x into AL. You can use any 8-bit register here, by the way. But for me, as long as AL is available to me, when I'm doing math, I'm going to use AL. And if AL is not available, then I'll just kind of start working down the alphabet. If AL is already being used for something, I'll use BL. If that's being used, I'll use CL, and so on. But for math, most of the time, until we start doing division, A is going to be the star of the show. All right, so middleman, we're going to sub AL from Y, which is Y equals Y minus X, which is being stood in for by AL. And then same idea. If you wait for another instruction to execute, E-flags is going to get screwed up, and it won't mean what you want it to mean. So you check flags immediately after the instructions that are of interest to you. So I'm doing a sub here. This could trigger a carry condition, so I need to check for this immediately. So I'm going to check for the carry bit, and I'm going to do the same kind of message. So the result does not fit in. I should have been saying, by the way, unsigned 8 bits. But when we are subtracting, this is our problem, is that we might get down to negative numbers, but you can't have negative numbers unsigned. So what does that look like? Well, let's find out. And then we will report on Y, and this is the last time I'm typing it before I start copying and pasting it a little bit else. Is yeah, and I'm getting fatigued on that, so I'm going to start copying it soon. So here we're doing a Y is 1 equals Y 1 minus X, which is 1. So is this one going to fit? It's is correct. This one's going to fit because 1 minus 1 is 0, and 0 is perfectly legal for unsigned 8-bit value. So let's confirm that. So the result is 0. That's expected. I'm going to do some copying and some pasting here after I do the setup. So let's change the setup. So Y is now 0. So let's make sure that... well, X is still 1. I don't need as much setup, do I? I'll let X remain 1. I will let Y remain 0. And then I'm just going to do the math. So set up the middleman, run the sub. And then I'm going to copy and paste this time. Okay, so we have Y, which is 1. No, Y is 0. Minus X, which is 1. So does this one fit? And if not, then... so Druid asked an interesting question. Will this trigger the sign flag? It shouldn't, because these are unsigned integers, so I don't think it's going to trigger the sign flag for unsigned integers. That should only happen when there are signed integers in the mix. So this one will not fit. We can check the sign flag just for fun and see if in fact that happens. So this one will not fit. And when you're doing subtractions, if it doesn't fit, it wraps around to the high end of the unsigned 8-bit integers, which would be 255. So if you take 1 off of 0, you force it to wrap around to 255. And by the way, that behavior of wrapping around is the same behavior that C++, as an example, does with integers. If you exceed the bounds by additions or subtractions, they wrap around on themselves just like they do in this class, which is quite interesting. So this wrapping around behavior is common. This is not the only place you will see this. Okay, so we should expect to see the carry bit and 255, which was true. So now Drew had asked, is the sign bit being triggered in any of this? Let's switch our view and let me get the sub page back. And let's see if, before we try it, let's see if we can get it from the documentation. Hopefully I switched. I did. Okay. So what are we talking about? Sub. Okay, so let's see. So the sign flag will indicate the sign of a signed result. So since our result is unsigned, the sign flag won't have any meaning for us. It's possible that it's set, but it shouldn't technically have any meaning for us because the result is going to be an unsigned result, which means the sign flag is not in the mix for this instruction. But it was a very good question to ask because that is pretty soon that we're going to start having that be in our mix of flags bits that we can check to see what's going on. Plus I got my sub page back. Okay, that is most of what I got. While I'm here, I'm going to go look at the module and the lab. So individual project 1 is due Sunday, October 9th. And I'm just telling you that now to keep it on your radar. But let's go look at the module and see if there's anything weird about the lab before we call it a day. So add and sub, you're going to see more procedures in the lab this week. So let's go look at the code and just see if there's anything funny looking about it. All right, so we have a couple of static variables we can use. Getting the easy greeting credit. So everyone got that, just, some dumb thing. But the reason these are here this way is it will make everybody's life easier if we get accustomed to seeing procedures in our code and then ultimately using them. For example, you can use them if you want to on your first project, although technically you don't have to. So these are just here to get us acclimated to the HLA procedure, which we will use because it's such a good technique for organizing code. Okay, so print greeting, that one's pretty straightforward. So get wager. So this is kind of a terrible vending slot machine simulator. You'll see what I mean when you implement it. So it's not meant to be a realistic slot machine. It's just a programming assignment, but I wanted it to not get too much. I don't want it to be too much of a grind, so I thought maybe this would be more interesting than just printing out numbers for everybody. Okay, the second problem is in the get wager procedure. So again, we're kind of being acclimated to what procedures look like using their parameters. So notice in this case, the wager is unsigned 16-bit and is using the AX register because of that. So you have to be thinking here. This is 16-bit stuff going on in this procedure. The documentation will draw your attention to that fact, but pay attention while you're coding it. So write a breakif here comparing AX, which is the input we're getting off of this getU16, with min and max, which are un16s, which means that you can do those comparisons. So 16 bits of everything, right? All right, so show symbol. So you're going to get a number as a parameter. So you will say if number equals 1, standard out dot put this thing. Else if number equals 2, standard out dot put this thing. Else if number equals 3, standard out dot put this thing, and that's it. That's that procedure. So it's just a little decision tree with some outputs based on this, the value of this parameter. Let's see, number 4. This one's already been done. The spin the wheel, but you can, if you want to, fiddle around with the probability distribution. And I've documented it to kind of explain to you how the distribution works. So if you want to play around with the different probabilities for cherries, money, and stars on your slot machine, you can do that. But this one's done. Oh, I didn't do the rand range thing. I'm going to carry that over. So I'll leave this for a few minutes on the video. Let's do that next week. Doesn't really matter for us this week. Okay, here's another procedure. This one has got something new in it. It's using local variables. And notice they're declared with the keyword var this time. And var is in HLA how you create what are called automatic local variables. So these variables are available to this procedure only. They are created when the procedure executes. They are cleaned up when the procedure returns. This is how you do local variables to a procedure. And what has to happen? Oh, so the whole point of this procedure is you have to determine the result. So you're going to have another if, else if kind of tree here where you're going to take the value. So these are being spun, which is really just they're being used to generate the random values 1, 2, or 3. So you have 3 wheels. So you're going to have if, for example, if wheel 1 equals 1 and wheel 2 equals 1 and wheel 3 equals 1, then the return value is supposed to be 1. So what this number 4 will look like is if wheel 1 equals 1 and wheel 2 equals 1 and wheel 3 equals 1, move 1 to AL. Remember, that's how we return values from a procedure, is we move the desired result into the desired register. So returns the result in AL. If they're all cherry, move 1 to AL. If they're all money, move 2 into AL. Else if they're all stars, move 3 into AL. Else move 0 into AL. So this one does not give you any points for having one wheel be cherry. They all have to match. Okay, so that's number 4. There's not anything super complicated about that. I emptied out the play again procedure, but it's exactly the same code. You can just lift it from last week's lab. The reason for that is because I've just discovered that it is helpful for some people to have that encouragement to revisit past labs and reuse things from them. So this is what this is here for. I'm encouraging you to go to last week's lab, lift code straight out of it, and reuse it here, which we're going to do a lot of in this class. And then what else is there? Number 6, that's a sub instruction, and it even sort of hints at using a middleman, so make sure the sizes match. The wager is an unsigned 16-bit integer, so the middleman has to be a 16-bit register. But it's already kind of telling you that. 7, here's another one. So tells you you're going to do an add and you're going to need a middleman, and it recommends you use AX for that. 8 is another one where you're going to do an add and recommends using AX as a middleman. Break if the player's money is 0, or they've chosen to play again. So this is going to be a logical or, checking their money being at 0, or the AL that you get from play again is false. And that's it. So I hope that you all find that this is just well and easily doable. But don't forget, Canvas Inbox, office hours, Piazza. Um, if you get hung on anything and you need tips to move past it. So all of that stuff about checking the error flags should not come up in this um, lab, but if you want to experiment with them, it's not going to hurt anything to go ahead and include them in there and see if you can cause them to be triggered in your test runs. So that's okay to do that, but they're not necessary for this lab. So if you don't do any of the carry flag checking in this lab, you will be just fine. But if you want to do the carry flag checking, you're certainly welcome to do so. Okay, that's the lab. The discussion, some people have already gotten in there and started on that, I saw. And then just don't lose track of the individual project, which is due on Sunday, October 9th, which is sooner than later, right? 2.5 weeks from now. So factor that into your planning. With that, I am done for the day. It's a little bit early, at least, for all of you. So thanks for being here. Thanks for interacting. For those of you who had the courage to do that, I really appreciate the help that you give me, and the interaction that we have gives me a better flow, I hope. And yeah, I guess I can. Yeah, I will post I'll post the code on the lecture page, and I'll also post the add and the sub documentation on the lecture page as well. But you can also just Google x86 add, and if you hunt around a little bit, you'll find websites that present to you how it works and what flags are set when and that kind of stuff. These I just thought were some of the more thorough ones, so I will link those on the lecture page also with the sample code. And that's it. So have a great week. I'll see you on Tuesday next week. Take care.